Welcome to AlgoStock, where we unravel the mysteries of data. Today, we are on a thrilling case to uncover the secrets behind three powerful tools: Ridge, Lasso, and Elastic-Net Regression. Imagine you're a detective trying to solve a puzzling case. You have a list of suspects or features, and you need the best tools to help you find the truth hidden in your data. But beware, each tool has its own tricks and traps. Will you choose Ridge, with its smooth moves? Or maybe Lasso, known for its ability to trim the fat? And what about the mysterious Elastic-Net, combining the best of both worlds? Join me as we investigate each tool, uncover their strengths, and discover when to use them. Grab your magnifying glass, and let's dive into the world of regression together. Linear regression, the starting point. Alright, detectives, meet our prime suspect, Suspect 2. This character is hiding some important clues, but things aren't always what they seem. Now, let's investigate how linear regression, our trusty tool, can sometimes get too close to the data, leading us down a tricky path called overfitting. To show you how this looks, let's pull out our magnifying glass and visualize the data on a 2D graph. Watch closely as we plot our data and see how the linear regression line tries to fit the scene sometimes too perfectly. Let's introduce some test cases. Those little gray dots. These represent new, unseen data. When we test it on these gray dots, things don't go as planned. Instead of predicting their true values accurately, the model gets confused. It struggles because it's too busy remembering every detail from the training data, leaving it blind to new situations. This is what we call overfitting, when our model learns the training data too well, but fails to generalize to new cases. Just like a detective who only knows the suspects but can't solve new mysteries. Let's dig deeper and explore how we can avoid this pitfall. Stay with me, detectives. RMSE, a detective's measure of success. Now that we've cracked the mystery of overfitting, it's time to assess our methods. Think of RMSE as our detective tool, helping us see how close our model's predictions are to the truth. A lower RMSE means more accurate predictions, like having a sharp eye for details. Let's use RMSE to see how well our models perform. Remember, accuracy is key. The numbers tell the story. RMSE discrepancies. Let's dive into the numbers. They tell us a compelling story. Our training model shines with an RMSE of 1.04, indicating it fits the training data quite well. This is great news, right? But wait, when we look at the test set, we see a different picture. The RMSE rises to 1.55. That's a red flag waving right in front of us. This higher RMSE tells us our model might not be generalizing effectively to new, unseen data. It's like a detective who knows the case inside and out but struggles to solve a new mystery. This discrepancy between the training and test RMSE is a crucial suspect in our investigation, pointing us toward the potential for overfitting. Our model may have become too attached to the training data, leaving it unable to tackle fresh challenges. Evaluating all suspects, features under scrutiny. Now that we have our lineup of suspects ready, it's time to bring them all into the interrogation room. Each suspect represents a feature in our dataset, and while creating a visual representation of each one may seem daunting, we can still gather valuable information from them. This method allows us to see the collective influence of all suspects, providing us with a clearer picture of the situation at hand. Are any suspects providing valuable evidence, or are some just distractions leading us astray? The investigation continues. RMSE and overfitting. After thoroughly interrogating all the suspects, we've discovered that the RMSE has reduced significantly to 0.06 for the training set and 1.54 for the test set. This improvement is certainly noteworthy, but hold on, despite this progress, we're still entangled in the web of overfitting. These numbers hint at a troubling reality. Our model fits the training data rather well, but the performance on the test set suggests it struggles to generalize to new cases. As seasoned detectives, we must ask ourselves, can we do better than this? Are there clues hidden in our data or techniques we can apply to help our model break free from the chains of overfitting? Analyzing the suspects, coefficients, and their influence. Now, detectives, let's shift our focus to the suspects themselves and see just how much influence each one truly holds. By examining the coefficients of our linear regression model, we can determine which suspects are most vocal in shaping the outcome of our investigation. These coefficients represent the weight of each suspect's testimony. Some might have a strong say, while others may whisper in the background. As we explore these numbers, remember that a higher coefficient means a stronger influence on the model's predictions. Which suspects are pulling the strings, and who might just be a mere bystander in this case. Let's analyze these coefficients to identify the key players in our investigation and understand their roles in the story we're unraveling. The suspects have spoken, and these coefficients reveal the weight of each one's testimony in the investigation. In this linear regression model, the coefficients represent the influence of each feature on our final prediction. Positive coefficients. These suspects are pushing the case in a certain direction, influencing the outcome positively. The larger the coefficient, the stronger their influence. If a suspect has a high positive coefficient, it means they're a key player, strongly driving up the predictions. Negative coefficients. On the other hand, these suspects are pulling things back. A negative coefficient means the suspect is working in the opposite direction. The further the coefficient is from zero, the more impact this suspect has on lowering the outcome. Small coefficients. These suspects have little to say. If a coefficient is close to zero, the suspect's role in the case is minor. They may still have an influence, but it's not significant enough to change the overall outcome much. In a sense, each coefficient tells us how much we should listen to that particular suspect. Now that we've unraveled their testimonies, it's time to consider how we can refine our investigation further. Stay tuned as we prepare to shift gears and explore how regularization can help us manage these influences more effectively. Tools of the trade: Ridge and Lasso Regression. To combat the ongoing challenge of overfitting, I turn to two essential tools in my detective toolkit: Ridge Regression and Lasso Regression. Think of Ridge Regression as a reliable ally that keeps all suspects in the running while helping me filter out the noise. This method imposes a penalty for model complexity. It ensures that each suspect's influence is tempered, meaning that even though all suspects are under scrutiny, their individual impact is diminished. This makes it less likely for any one of them to mislead my investigation. In contrast, Lasso Regression takes a more decisive approach. This tool not only reduces the influence of suspects but has the power to eliminate some entirely. Known as L1 regularization, it applies a penalty to the absolute values of the coefficients. It effectively signals to me, these suspects aren't worth your time. Focus on the crucial leads. Together, Ridge and Lasso enable me to sift through the clutter and hone in on what truly matters in my investigation. Now, let's visualize this unfolding mystery and see how these techniques reshape our understanding of the case. The case of the unstable coefficients. Enter Ridge Regression. Detective has been summoned to investigate a case of overfitting. The model is spiraling out of control. Too many coefficients are taking extreme values, leading to unreliable predictions. The detective must tame these wild coefficients before the model collapses under its own complexity. Enter Ridge Regression, a method known for shrinking coefficients, allowing the detective to regain control over the situation. Ridge Regression addresses the issue of overfitting by adding a penalty proportional to the sum of squared coefficients. It prevents the coefficients from growing too large, stabilizing the model and improving predictions. Understanding loss and regularization. In Ridge Regression, the cost function in Ridge Regression with the L to penalty is on the right. This is the loss term, which calculates the total error between the predicted values and the actual values. It measures how well the model is performing. A smaller value means the model's predictions are close to the actual values. This is the regularization penalty term that helps to shrink the coefficients to prevent overfitting. This term discourages large coefficients, which could lead to overfitting. It does this by adding a penalty proportional to the square of the coefficient values. The larger the coefficients, the larger the penalty. As lambda increases, the coefficients shrink more. In short, I'm not just trying to minimize the prediction error, but also adding a layer of caution. Ridge Regression helps me avoid over-relying on any single piece of evidence. Bringing back suspect 2. Our MSE did not change after applying Ridge Regression only to a single suspect, but we have some important clues to consider. This could mean that suspect 2 may not be as influential as we initially thought. Additionally, it suggests that Ridge Regression might not work at its full potential with such a limited number of suspects. What if there are other suspects that might hold more weight in the investigation? Let's keep digging deeper to uncover the truth. Penalizing all suspects together. With Ridge Regression, Let's apply ridge regression to all suspects together by distributing the penalty across all coefficients and compare the lines fitted with ridge regression against those from our simple linear regression model. This will help us determine if penalizing all suspects together can effectively prevent overfitting and lead us to clearer conclusions. Ridge regression results, RMSE. Applying ridge regression to all the suspects brought some interesting results. While the RMSE for the training data increased, the RMSE for the test data decreased. What does this mean for the investigation? Train RMSE increased. This indicates that the model is not overfitting the training data. Comparatively, by penalizing large coefficients, Ridge ensures that we introduce some error into the training process to prevent overfitting. Test RMSE decreased. This is a positive sign that our model is now better at generalizing to new, unseen data. Ridge has reduced overfitting and improved the model's ability to handle test data. These changes tell us a powerful story. By penalizing all suspects together, we've managed to create a more balanced model, one that respects the evidence without letting any single suspect take over the case. What happened to the coefficients? Ridge regression has effectively shrunk the coefficients of all features. Thanks to regularization, we've ensured that no single feature wields too much influence over the outcome. This results in a more balanced model, where each suspect has a fair chance to contribute to the investigation. Some suspects, which might have boasted overly large coefficients in our initial analysis, have been reined in. The uncertainty of lambda in ridge regression. As I delve deeper into ridge regression, one crucial element remains uncertain: the value of lambda. This parameter determines how strongly ridge penalizes the coefficients, but there is no fixed method for selecting its optimal value. A small lambda might lead to overfitting, where the model captures noise in the training data. Conversely, a large lambda may result in underfitting, causing the model to miss out on important relationships. The solution: trial and error. To uncover the best value for lambda, I must test a range of combinations to see which yields the least error in predictions. This trial and error process is essential for finding the optimal balance, similar to a detective sifting through evidence to find the right clues. Let's prepare to explore various values of lambda and identify which one unlocks the best performance for our ridge model. As I tested various lambda values, I observed a clear trend. As I increased the penalty on the suspects, the RMSE root mean square error began to rise. This finding aligns with my detective instincts. Over-penalizing the suspects can lead to a loss of vital information. While we want to keep the noise in check, we also need to ensure that we're not hindering our model's ability to learn from the data. Introducing Lasso Regression, simplifying the investigation. Now that we've sharpened our skills with ridge regression, it's time to bring another powerful tool into the investigation: Lasso Regression. This technique has a unique way of tackling the suspects, allowing us to streamline our focus. Lasso least absolute shrinkage and selection operator adds a penalty proportional to the absolute value of the coefficients, shrinking some to 0. This makes it ideal for automatic feature selection, the cost function for Lasso regression. This is the loss term, just like in ridge regression. This measures the accuracy of the model's predictions. A smaller value means the model's predictions are closer to the actual values, reducing error. This is the regularization penalty term, but in Lasso regression, the penalty is based on the absolute values of the coefficients. This term penalizes large coefficients by shrinking some of them to 0, effectively removing some features from the model entirely. The L1 penalty forces the model to focus only on the most important features. As I apply Lasso, I witness irrelevant features beginning to vanish, leaving only the most critical suspects in play. This process simplifies my analysis, making the case clearer and easier to solve. Understanding why Lasso eliminates suspects, a geometric interpretation. To understand why Lasso is so effective at eliminating suspects, I need to dive deeper into the math behind its penalty. Let's narrow down our focus to just 2 suspects and visualize how Ridge and Lasso penalize them differently. Ridge's interrogation room. The penalty constraint takes on a circular shape. Imagine a circular room where Ridge is questioning both suspects. The closer they are to the center of the room, the less involved they are in the crime. The closer their coefficients are to 0. The plot shows circular contours. Each contour is like a pressure level that Ridge applies to the suspects. As you move inward, Ridge reduces the suspects' involvement, shrinks their coefficients. but no one reaches zero. They just get pulled closer to the center without being eliminated. Both Theta 1 and Theta 2 stay in the game. Ridge won't let them walk out, even if they've become insignificant. Lasso's interrogation room. The penalty constraint is a diamond-like shape. The room now feels different. Sharp edges line the walls, shaped like a diamond. The diamond-shaped contours reflect how Lasso operates. They're sharp, meaning some coefficients get zeroed out when they hit the axis. If a suspect, say Theta 2, drifts close to the axis, Lasso is more likely to push them all the way to zero. As I increase the value of lambda, the available space for the coefficients decreases. In Ridge, this squeezes the suspects evenly but keeps them all in play. In Lasso, the diamond shape forces some coefficients to zero, making Lasso ideal for eliminating unimportant features. Lasso's performance. A step forward. After running Lasso on my full lineup of suspects, it's time to compare the results. Although it successfully removed some irrelevant suspects, the overall RMSE for both the training and test sets didn't dip below Ridge's performance. In contrast, Ridge outperformed Lasso by keeping all suspects in play but reducing their influence evenly. This approach led to a better balance between the training and test results, making it a powerful ally in our investigation. It's also worth noting that Lasso did outperform plain linear regression. Lasso was able to control overfitting by eliminating unnecessary suspects, unlike linear regression, which allowed too much noise to interfere with the case. These results reveal a crucial lesson. Lasso can be more efficient when we have many irrelevant suspects to eliminate. However, in this scenario, Ridge proved to be the superior method since the relationships between the suspects were too strong for Lasso's feature elimination to shine. Investigating Lasso's impact on coefficients. Now, let's examine how Lasso has impacted our suspects, our model's coefficients. While it may not have outperformed Ridge in RMSE, Lasso's true strength lies in simplifying our case. Lasso effectively pushes some suspects out of the picture entirely, leaving us with only the most crucial leads. This means our model becomes more efficient and easier to interpret. By reducing the influence of certain suspects, Lasso helps us focus on the key players that truly matter in our investigation. It's like having a sharp eye that sifts through the noise to highlight what's essential. Experimenting with lambda. Just like in Ridge regression, the value of lambda plays a crucial role in Lasso regression. A higher lambda forces more coefficients to zero, leading to a simpler model, but risking the omission of important features. Conversely, a lower lambda keeps more suspects in play, which can lead to overfitting and complicate the investigation. To find the optimal value of lambda, we need to experiment with different settings. This iterative process will help us discover the lambda that yields the lowest RMSE. The best of both worlds. Elastic-Net Regression. By now you must be wondering, what if we could combine the strengths of both Lasso and Ridge regression? Wouldn't that give us the best of both worlds? Well, the answer lies in a powerful ally in our detective toolkit, Elastic-Net Regression. Elastic-Net takes the regularization techniques of both Ridge and Lasso and combines them into one unified approach. This means it can shrink coefficients like Lasso, effectively eliminating irrelevant suspects, while retaining the most important ones. Handle multicollinearity like Ridge, ensuring that when suspects are correlated, they are still appropriately managed without being completely discarded. This hybrid approach is particularly useful when we have many features that are highly correlated. Elastic-Net can pick up groups of correlated suspects, ensuring that the model remains robust while simplifying our case. Performance. Elastic-Net Regression performed better than Lasso but not as well as Ridge, which makes sense given its approach. Elastic-Net combines the strengths of both methods by using both L1 and L2 regularization, offering a balanced technique. To achieve optimal performance, we must embark on a quest to uncover the best value for this mixing parameter. This involves running multiple trials and analyzing the outcomes much like a detective revisiting clues until the overall picture becomes clear. Clearly, lower L1 ratio gives best performance because Ridge outperformed Lasso in our data. Common mistakes and misconceptions in regression techniques. As you navigate the intriguing world of regression analysis, it's important to be aware of common mistakes and misconceptions that can arise. Here are some key points to keep in mind. A common misconception is to apply regularization to the intercept term. Do not regularize the intercept. Always leave it unpenalized, as it represents the baseline value and should not be influenced by regularization. which is meant to handle the coefficients of predictors. Some may think that the regularization parameter, lambda, can take negative values. Lambda must always be a non-negative value. A negative lambda would effectively reverse the penalty, which contradicts the purpose of regularization. This would lead to uncontrolled overfitting. Believing regularization fully handles outliers is a common misconception. While Ridge and Lasso help reduce their impact, outliers can still distort results. Always inspect your data, and if outliers are a serious concern, you may need additional methods like robust regression. There will be a separate case on robust regression, link in the description. Conclusion: unraveling the mystery of regression techniques. As we conclude our investigation into the world of regression techniques, it's clear that each tool in our detective toolkit serves a unique purpose, helping us solve different types of cases in data analysis. Linear regression is your go-to for simplicity and clear insights into relationships between variables. It lays the groundwork for understanding your data but can fall victim to overfitting, especially when faced with complex cases. Ridge regression steps in to handle multicollinearity and reduce overfitting by applying L to regularization. It allows you to keep all suspects in the running, ensuring that no valuable leads are overlooked. However, it doesn't perform feature selection, which can lead to unnecessary complexity in the model. Lasso regression takes a more aggressive approach by eliminating irrelevant features through L1 regularization. This results in a more streamlined model, enhancing interpretability and focusing on the critical suspects. Yet, it can introduce bias and lead to inconsistency in variable selection across different datasets. Finally, Elastic-Net Regression combines the strengths of both Ridge and Lasso, offering the best of both worlds. By fine-tuning the L1 ratio, it allows for flexibility in balancing feature selection and multicollinearity handling. This method is particularly beneficial when dealing with datasets where predictors are highly correlated, or when you suspect that only a few features will be significant. In summary, the choice of regression technique should be guided by the specific characteristics of your data and the objectives of your analysis. Armed with these insights, you're now ready to tackle your own data mysteries with confidence. If you've enjoyed today's investigation or uncovered something new, don't forget to hit that subscribe button. Join me on this journey as we crack more cases in the world of algorithms and data. There's always more to learn, and I'd love to have you along for the ride. Until next time, detectives, keep learning, stay curious, and never stop exploring the clues in the world of algorithms.